Okay, so good morning. So today we will start, our statistical mechanical study of the van der Waals gas. So the first step to doing that is to compute the free energy of the van der Waals gas, and we'll connect up to some general formula which is called the virial expansion, which we will see again. So the virial expansion is a systematic expansion where where we study corrections to the ideal gas law. Okay, so for instance, if you have a quantum ideal gas, even if there are no interactions, you will find that there will be deviations from ideal gas behavior for quantum gases. So quantum Fermi gases, quantum Bose gases behave very differently. Okay, and we'll see all these things. But right now we're doing something very, very simple. And so I'm just flashing the van der Waals equation of state. And the only thing to remember is that there are two parameters, free parameters, and we will see how to interpret these two parameters, okay, and where they come from. So don't worry about the horizontal lines. That's the Maxwell tie line. We will discuss that also, either here or somewhere else. Okay. So here I have so all these plots are for for t less than or equal to Tc. So the first curve is the topmost curve is the case. So t decreases as we go this way. Okay, so this is decreasing t. Okay, and so this curve is exactly t equal to Tc. Okay, so what we see here is that you can see an point of inflection somewhere here. Okay, and so so this is one of the plots that I want you to do, including the horizontal lines, of course. Okay, that's where the money is in some sense. Okay, so obtaining okay, so we'll just do the standard computation of the canonical free energy, and okay, so that's what we want to do. And so yesterday actually, so we need to have a potential. So we need to interparticle potential. Okay, which we will take to be spherically symmetric. This is for us, it's a simplification. So we write this u of r, where r is the distance between the two particles. Okay, so we need to pick a potential, and I'll draw the van der Waals potential. So let's do that. Okay. U versus R for VDW. Okay, so up to some R naught, there is a barrier. Okay, so maybe I should do it better. And then it's attractive, so I take it to some negative value, and then it goes to 0. Okay, so yesterday, oh, I drew something where it was attractive to all this thing. So actually, that feature is not quite correct because we need it to. You'll see that it has to go to 0. I'm not drawing a great curve, but you see that. And so some features are that this is the attractive part, and it goes to 0 as r tends to 0, infinity. And this is a barrier, so this was r naught. So there's infinite barrier, infinite barrier. Okay. Okay, so this R naught could be, so it says that two particles cannot come closer than some separation R naught. So if you picture them as, two balls, then this distance can be thought of as R naught. Okay, they can't come any closer. Okay, so it gives us, this is off to infinity out here. Okay, so is this clear? So this is the van der Waals potential. Okay, so we won't need much details beyond this. Okay, so now we want to compute. So we'll do the standard thing. So the free energy will be integral 1 by, we'll put this n factorial, the Gibbs factor, 1 by h power 3n, because it's a semi-classical computation, integral pi equal to I equal to 1 to n p cubed pi p cubed ri. Okay. If there's anything which I'm writing here which is not obvious to you, please let me know. And I wrote this last lecture also. These are identical particles and u of I. So if you're talking about the van der Waals thing, so that would be the example which you can have in mind, but we won't need too many details about your R beyond. Okay, so is this clear? So this is the computation that we need to do. Is there any term in this? Oh, this is not correct. U of R is wrong. I need to write a sum, infinite sum if you wish. I less than j, and sum over all i's, u of rij. Is this clear? So we are just assuming pairwise potentials. So this is what, so we need to do this computation. Okay. So if you remember, in the absence of this, we got this, and I've written F here. Does this make sense? Is this the free energy? Oh, it is like at the end of Ramayana, you are asking me who is Sita, kind of thing. So what I'm asking you is, I'm computing some object. So I think this is not correct. I wrote something because my writing was not keeping up with my brain. Yeah, that's all. That's all. Okay. So that's not, simple. Okay. Don't think it is some deep thing. Usually it's me making a mistake. That's all it is. This is the partition function. So f is minus k b t log z. Okay, these are things which. So this, we have done several examples of this variety. Okay. So the ideal gas is when we put u is 0. That's it. Okay. VDW gas, u equal to u VDW. That's it. Nothing deep. Okay. So there is one set of integrals which are easy, and which one is that? Anybody? D3R we have to integrate over e power minus beta ur, right? Momentum integrals. Each of them for each component is a Gaussian, so you just, okay. So we can do easy integrations. The dqpi for all I. Okay, and I don't expect you to remember all those things, but anyway, z would be 1 by n factorial. So I'll do that. I'm not going to explain this. Hopefully I don't make a mistake. times, now I need space. It's not fun when you run out of space and I have to now split it over 2 pages. No, I'll write it below this. Okay, sorry. Okay, this is the integrals we have to do. Okay, so we have a what 4 pi? All that I have finished. This was the answer. 4 pi, etc. Everything got done. Everything is gone. So I'm not showing the details. If you remember, when u was 0, this x integral was easy to do. It gave v power n. And that log, if you did minus kb log out of that we got the Helmholtz field energy. All the 4 pi's, etc. I've taken care of. Okay. So I'm not doing the momentum integration for you. Okay. Along the way, some 4 pi will come. All those things will come. Okay. Either that or you can do each P1, P2, P3. Each is a Gaussian. Each will give 2 pi m kbt square root. That's all. So there are 3n of those guys. So each of them will give that. So that is this. Okay. So we need to carry out the spatial integrations. Okay. And that's not simple. Okay. But so people use a variety of expansions. Okay, so you will hear nouns like cluster expansion, for instance. Okay, and some beautiful pictures and some beautiful diagrammatic ways of organizing the expansions. Okay, but we won't need all these things. We will just do something extremely simple. Okay, so that's what I want to do. So what is the integral I want to do? So the integral I want to do is a 3n-dimensional integral. So pi I equal to 1 to n d cubed xi. Okay, e power minus beta times I less than j u of rij. This is what I need to do. Let's not overdo the I index because it's already used here. So I'll use jk. Okay, so we need to do this integral. And what we will do is we'll define something. So define, you'll understand it. We will define Fij. This is just definition. Okay. It's not just this, but it's e minus of 1. Okay. So what that implies is that e power okay, so now I can, let's call this integral I. So I becomes integral by I equal to 1 to n d cubed xi times product of j less than k. So each of these ui terms here will give you a product because it's in the exponential. So is this clear? Okay. So what happens here is that if you look at the structure of this thing, so this -1 is actually important. What it does is, it's a mathematical statement. It improves the convergence properties. Okay, and so the convergence properties will also depend on properties of U, such as it goes to 0, for instance, as R goes to 0, so that you get things which are convergent. Okay, so that's also part of the D. So we need to do this thing, and so what you do now is expand this product into bunch of terms. Okay, so we do that. Yeah. What was the 1 plus lambda? No, scaling. Those scaling arguments. No, it has nothing to do with it. It's just simple-minded reorganizing of things. No, it is not that. It's definitely not that. Okay, so then this is fine. Okay, times. So I can expand this. And there will be higher order pieces, and this is where there will be terms with multiple f's, f, j, k, f, k, l, etc. So okay, so additional terms. But for our analysis, I'm just going to take the first set of terms. Okay, so this is what we have. Okay, so first thing to observe is that since we are integrating over all the coordinates, each of these terms, each of these guys will give the same answer. So I can write this as equal to, and how many of them are there? N into n minus 1 by 2. And pick any value of j and k. So let's just say f12. Is this point clear? I'm just using the fact that they're all identical things, and if I just think so, I just compute one of them and multiply it by n into n minus 1 by 2. F12 is not, there's nothing special about 1 and 2, but it just doesn't. Okay, so that's what I will do. So then you can see that this is equal to, now I can do the integrations. First one is d cubed xi into 1 plus n into n minus 1 by 2 into d cubed. No, nothing. J less than k, j and k take n values. How many independent terms are there? There are n into n minus. Even if you come back to the Hamilton, look at this. There are n into. So you're considering a pair of particles. You have a number of ways you can pick two particles from this thing. You don't care if which order in which it's picked. So it's n into n minus 1. So first one you can pick any one, n ways, and then the second one should be done in n minus 1 ways. But the dividing by 2 is because I could have picked the first one first or the first one second. That's it. That's just a standard concept. It's just a combinatoric factor. Times f. Okay, so this is what we get. Okay, so now we can do these integrals. So now the question to you is, what is the first integral? So there are two integrals now. First one is very easy. Okay, almost correct. Okay. Okay, but this is where we need to, but there is some exclusion volume. Okay, so the fact that there is some volume which is not allowed, so that would be V minus some, we'll call it B for now. Okay, because No, this is not quite correct. So I should write it correctly. Okay. So what is NB? If you remember this picture, because this region is not allowed. Okay, so they cannot come closer than R naught. Okay, so this B, so you can estimate, but what I want to say is B is proportion is some constant times R naught cubed. Okay, you can argue that each particle is occupying R naught by 2, so 4/3 pi R naught by 2 whole cubed. If you did that, you'll get some value for the constant, but I'm not particularly interested in that details. All I'm saying is that B has to be, so this is the excluded volume. This is clear? Okay, and then, yeah. So each particle, so each d cubed x, say take the first particle, okay, it can occupy a volume which is, if you want, it's d cubed, so it can only take the but there are n minus 1 other particles. So maybe I should be even more pedantic and write n minus 1, but n is supposed to be large, so I don't worry too much about n minus 1. Eventually here also we will forget about this one. Okay, so what it says is that if you have some, I'll draw some picture in this. Suppose there were 4 particles. Okay, so what is the accessible volume for this guy? This all of them have some volume. Okay, so this say particle 1, 2, 3, and 4, and this total volume is V. That we have to subtract this, right? It can't. It doesn't have the if you wish, the interparticle repulsion tells you that it can never get closer to 2, 3, and 4 than R naught, right? So this is the exclusion. So it is like they have. I mean, it's simplest to think of R naught by 2 as the size of each particle. Okay, so that's the excluded volume. So we are taking into account the fact that this thing has this thing. So now this integral is done. Okay, so now we have to do the next integral. But now f12 is only a function of R12. Okay, so we can just go ahead. Okay, and so let me assume large n, and I will now make I'll write n square by 2, and so we can do n minus 2 integrations, and they will also give b minus nb over n minus 2. Okay, so then we are left with d cubed x1, d cubed x2, f12. Right, this is what we have to do, which is only a function of R12. And so to do this integral, we have to do change of variables, etc., etc. So we need to go to, from this, we change to, we can go to center of little r is, if you wish, x1 minus x2, and capital R is x1 plus x2, something like this, right? Center of mass, so by 2. Okay, so then integral d cubed then you get so what we get is integral d cubed x1 d cubed x2 is equal to integral, this you can check Jacobian is. Okay, so this is true. So then I can do this integral, and this will give me another factor of, say, v minus n. Okay, so we get, so I'll put all these. So what I'm doing is I can do the capital R integral, but then I'm left with one integral that has to be done. Okay, so we get I equal to, that's all. Okay, so this is the integral. Is this fine? Hello? Am I connected? Okay. So I've just put these things together, nothing. So I have, yeah, yes. Which one? Oh, so yeah, so there might, it's just, I'm just doing it somewhat approximately. Yeah, I mean, I'm just saying that it'll give, but it'll be something which is proportional to V. I mean, so I'm just, yeah, so we are not doing some great exact, precise, because we can't really do the precise computation. So yeah, you're right. So this is an estimate. Okay, which is not bad. I mean, you agree with that, right? Okay. Yeah, we could pick nits and things like that. That's okay. So then we can rewrite this whole thing as b minus nb power n, okay, plus n square. So now, yeah, n square by 2. I don't know what I wanted to do slightly different. Okay, into 1 plus, and there are a whole bunch of terms. I'm throwing away so many terms. Okay. Now again, I will throw away. I'll just write it as 1 by v. I could, maybe I don't have to throw it away. That's at least. Okay. So it's important to realize that here, right, f of r is, go back and remember, f of r is e power b minus beta u of r minus 1. Okay, so this has some temperature dependence. So this is what the structure is. So now we have, so we can put this all together and we get z equal to 1 by n factorial. Okay, so it's 1 by n factorial into 2 pi m kbt by h square power 3n by 2 times v minus nb by n into, okay, okay, I've truncated the rest of the terms. Okay, so this is what we get. Okay, so I need to identify what a is. Okay, so how do I do that? So, no, it doesn't matter. So f is minus kbt log z, and then we will of course take n being large, and n factorial you will replace with n log n minus n, so on and so forth. Okay, and exercise. Okay, and simplify. Okay, so I'll just write something and then we can argue what that is. Okay. So this is the term, you can see, minus okay. So this is what it is. So now we can just compare, look at this, and if you do a little bit of work, so log of 1 plus something is what is it I wanted to say? Yeah. So I have to make this work. So I'll do one more simplification. So we need to identify compare A with the integral okay. So I'm not proving that, so I'll just show you this. So what I will do is so first thing is I will if you can see that I can throw away this nb, so I get this n square by t term, so that then I get this half. So A will be no, I still need to do one more simplification. So we need to do this integral d cubed r f of r. Okay, but this is pretty complicated, so we'll approximate it further. And this was just integral d cubed. No need to approximate. First, I won't approximate. I write the exact formula. So e power minus beta u of r minus 1. So what you do is expand this and keep only the first term. So this is now approximation. Okay, so this is integral d cubed r, the ones cancel away, times minus beta. Okay, so and if you wish, you can do the you can write 4 pi integral d cube, because we have spherical symmetry in our problem, we can write it like this. Okay, so now it's a little bit more. So now I just do things in my head. I hope you don't mind. So I get log of a product of things. We have to do log of that thing, but log of something is small. So that will just tell you that a. If you remember, there's a minus kbt. There was a minus kbt coming from the log z. That when it multiplies this beta, it will go away. So a will be half. There's a sign, possible sign, but let me just write this. Okay. And since we can even make this integral up to r, because that's where u of r is not 0. So this is what we get a. Okay. So now so we have actually now so we have some microscopic picture of the parameters a and b. Is this clear? So a knows about the a is the full integral from r naught to infinity, so it knows about that. So it knows about the potential. B knows about the exclusion volume. So that's a small this thing. So these are the two effective parameters which come out of this thing. Okay, so now we have got the free energy, and now we should get the equation of motion. how do we get the equation of motion? Yeah, exactly. From the free energy. Okay, so now we can obtain the equation of motion by computing uh, pressure. Okay, and what was pressure? Pressure was my df by minus df by dvi plus. Equation of state of motion. Thank you. Okay, and you just go ahead and do this. Lo and behold, okay, do the differentiation and obtain the VDW, the equation of state. I don't know about you, but I think it's pretty cool. So let's come back and look at this. So you see, if you put A and B equal to 0, it's a Sackur-Tetrode or whatever that we had formula which we had written long ago. Okay, and so then if you look here, where are the correction terms? That's a B here. And this is here. Okay, so let's just see, look at what happens from this term. So we can visually see this thing. So minus df by dv so there's a 1 by v. So integral thing will become minus 1 by v square. So this minus sign will go away and you'll get n square by v square. So you'll get p. So this will come to the other side and become p plus a into n square over v square, which is what we had. Hopefully, if I didn't make any mistakes in writing, that's what we had. That is this term, right? And then only way the way v is appearing is with v minus nv, so that gives you the shift. So it's basically the same answer as before. Okay, is this clear? So there's not too much work to be done to obtain this thing. Okay, so I'll pause here for a minute or two so that you can ask questions about what we did. We just followed our nose, right? Whatever we did for the ideal gas, but we just put in some potential, and we really didn't use too many properties of that potential. Okay, and so this gives you some picture of what the various contributions and how to get the van der Waals equation of state. Okay, are there any questions? Oh yeah. So absolutely. So that's the next thing. A very, very good point. So we neglected, the f square, f cubed, f power 4, all those terms. They're all there, and they can all be collected together into an expansion, which is what I'm going to discuss next. So so in some sense, what Van der Waals equation of state does is to get the first correction, it is Paka. It doesn't get the rest, correct? Okay, and remember last class somebody asked me what about solid, etc. If you want to get even the solid, if you want to even see the solid liquid solid transition come, you will require higher virial coefficients or whatever they are. Higher terms in the expansion will also be needed. Okay, so yeah, very good point. I will try. Yeah, you know what's happening? My this thing, the mic is adjusting on its own. So now I'm talking to the laptop. Now I turn here. Now I'm talking to my writing pad. There's a 40-degree angle between the two. So is this worse than say this? And then when I stop and start it, this thing's okay. Okay. So Oh, I understand. Yeah, it's doing something. It's doing something. I can see it automatically fluctuate. So, but without noise cancellation, it's so noisy. I don't know what to do. So, okay. Yeah. But that is because Google was doing it for me. Now this is some software on my computer. So I have to do something. So, okay. And I mean, Google recording was perfect. I mean, even this semester, I didn't have to worry about these issues, but now I have to. Okay. So it's doing something weird. Okay. Yeah. And I have a suspicion that the recording will be better than the live in some situations. Yeah. Go ahead. Somebody. So, the best we can do is hybrid because not everybody is going to come. Okay. So, yeah. So I have to figure out how to work that out. Yeah. So we'll work something out. Okay. Okay. So in the next 5-6 minutes, we will discuss something called the virial expansion. Okay. And so the virial expansion, I'll write out what it is. So it's just so I make some definitions. V is capital V by N. Little n is capital N by V, which is also equal to 1 by V. Okay. So So this would have been 1 for an ideal gas, but then you start getting terms which are temperature dependent times density, so on and so forth. Okay. So this is a power series in n with coefficients as functions of t. Okay. So now Bera asked, what about the next term, right? So f. So suppose we have a term like where can we get where can an n square type term come? Okay, so if you look at a term like this, f12, f23. Now this will involve three integrals. Okay, so now we'll have to do some integrations in this funny space, and the rest of them will give you v minus. So previously we got n minus 2, and now we'll get n minus 3. And then we'll have to do some little bit of go to center of mass, do all those things. And then you will, so this, a term like these integrals will be triple integrals, will give such a term. Okay, so this is called the virial expansion, and these are called the virial coefficients, the b's. Okay, so the b n of t, these are called the virial coefficients. Okay, so and we have computed in some sense since we only start. So effectively we have only computed not the first, second, because the first is 1. Okay, so you can go ahead and take the Van der Waals thing and rewrite it, Van der Waals equation of state, and rewrite it in this form and do the expansion, and you will find what you will find is that B2 of t is equal to B minus A times KBT. And you might find some terms which will go like n cubed, etc. But what I want to tell you is that those are not probably not we have missed out so many terms, so we cannot say anything better than this. Okay, so we can only extract this thing. So VDW gas does not do a good job of getting the higher virial coefficients. Okay, so it's not good if you just take that thing, it won't be getting V3 correct. Okay, so this is one coming back to this expansion, you can see we can this also I mean you must have heard this thing that at low densities, which is n being small, or high temperatures, okay, the ideal gas law holds. So you can look at this. This is a power series in n. Okay, so if n is small, you can see that the corrections become more and more in control. So 1 is good enough if n is pretty small. And if you look at B2 of t, in addition to it says high temperatures, you can see it's really a function of 1 by t's. Okay, so you can see again for large t also B2 of t becomes, so this A term will be pretty small. So these are the, so you can see that at high temperatures as well as and low densities is when we expect for any gas, we expect ideal gas behavior to be a reasonable approximation. Okay. So, but as you come down and things like that, but what is good about the van der Waals equation of state is that even though it doesn't get the higher virial coefficients correctly, it gets the fact that there is a liquid gas. Okay, it gets the liquid gas coefficient right. Okay. However, it gets the liquid gas phase transition. Okay, so since so there is a critical temperature, then you can ask about, you can define exponents like we did alpha, beta, gamma, delta, like we did in the case of the mean field approach, and you can compute the exponents for the van der Waals gas because you have the full free energy, like we okay, and then just go ahead do the computations, and that's what your next problem set is. It's a bunch of calculations and a couple of graphs to draw, and so what you will find at the end of this computation is that the alpha, beta, gamma, delta that you get for the van der Waals gas is identical to that of the mean field thing. So alpha, if you remember, alpha was 0, beta was half. Same, we will define similarly. We will define alpha, beta, gamma, delta. And if you think in terms of order parameters, it will be exactly that, and you will find it's identical to that. But real gases are much more. They live in 3D, so the critical exponents. So again, van der Waals gas is as good as mean field theory was for the magnet, and the correct exponents, if you wish, are that of the 3D icing model. So it's in the universality class of the 3D icing model. So I'll kind of stop here, and next lecture we will discuss in some more detail the phase transitions and how it connects, how these two, how this is like a mean field, etc. Okay, so I'm done for today. So open for questions. Mm-hmm. Yeah. So the correct statement would be that what we really want is B2 times n should be small. Yes. It's a very, very, very ill posed statement. So yeah, mathematically it's imprecise. So this does not answer, So we need more details to make the statement. Okay. I agree with that. Oh, I just said the R integration will give you a V minus NV, and then he said that you will have these issues So it's like how close it can come to other particles and all. I mean, these issues come. So I'm just saying that I'm not worrying too much about all those things. Just saying that it's effectively V minus NV. That's it. Okay, it's just an approximate. Okay. Yeah. Mm-hmm. Mm-hmm. What are the days? Mm-hmm. Mm-hmm. Yeah. So Tuesday is anyway optional. Nobody comes, so it's okay. Yeah. so so what I will do is we'll have nothing on Tuesday. On 9th we will have a like, class come tutorial. So it will be based on the problem set. So what I'm saying is there will be nothing on 8th. Okay. And there is no mini test next week as people asked. But on 9th I will take the lecture, but it will be, we'll work through the problem set. Huh? That's the plan.